Tonight, imagine yourself somewhere far from city lights. The air is cool and still. Above you stretches a quiet river of light, faint but endless, arching from one horizon to the other. This pale glow is not a cloud and not a dream. It is our home galaxy, the Milky Way, seen the way humans have seen it for tens of thousands of years. Long before telescopes, before science had names for stars and galaxies, people paused under dark skies and noticed this soft band of light. Some thought it was milk spilled by the gods. Others believed it was a cosmic road, guiding spirits across the night. Across cultures and continents, the Milky Way inspired stories, travel routes, calendars, and a sense of wonder that still connects us today. If you are listening now, you don't need to stay awake. Let your breathing slow. Let the words drift gently past you. This is a calm journey through our galaxy, told slowly, carefully, and with curiosity rather than urgency. If you find comfort in this kind of peaceful learning, you're welcome to like and subscribe, but only if it feels right for you. And if you wish, you can share in the comments where you are listening from, what city or country you call home, and what time the night has reached for you. Now, let us begin drifting outward. The Milky Way is a galaxy, a vast system of stars, gas, dust, and dark matter held together by gravity. It contains hundreds of billions of stars, possibly more, each one with its own story unfolding over millions or billions of years. Our Sun is just one of them, quietly orbiting the center. Along with countless others, from Earth, the Milky Way appears as a hazy band because we are inside it. We are not looking at the galaxy from afar, but from within one of its spiral arms. The light we see is the combined glow of distant stars, blurred by interstellar dust that softens and dims their shine. The Milky Way is shaped like a flattened disk with a central bulge. If you could see it from the outside, it would resemble a delicate spiral, with arms curving outward like slow-moving pinwheels. These spiral arms are regions where stars are born, where clouds of gas collapse under gravity, igniting new suns. Our home is located in a smaller spiral arm called the Orion Arm, sometimes known as the Orion Spur. It lies between two larger arms, the Perseus Arm and the Sagittarius Arm. This quiet neighborhood gives us a relatively stable orbit, far from the intense radiation near the galaxy's core. The galaxy is enormous. Light, which travels faster than anything else we know, takes about 100,000 years to cross from one side of the Milky Way to the other. When you look up at the night sky, many of the stars you see are not as they are now, but as they were long ago. Their light has been traveling through space for years, decades, or millennia before reaching your eyes. At the very center of the Milky Way lies something both mysterious and calm in its own way. A supermassive black hole known as Sagittarius A*. It has a mass millions of times greater than our Sun. Yet it is relatively quiet compared to black holes in active galaxies. It anchors the galaxy with gravity, guiding the orbits of stars far beyond its immediate reach. Despite its name, a black hole is not an empty void. It is a region where matter has been compressed so densely that gravity becomes overwhelming. Around Sagittarius, stars move in graceful, predictable paths, revealing its presence even though it emits no light of its own. The Milky Way is not alone in space. It belongs to a small family of galaxies called the Local Group. This group includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies that orbit larger ones. Over vast spans of time, galaxies interact, drift closer, and sometimes merge. In about 4 billion years, the Milky Way and Andromeda are expected to collide and slowly combine into a new galaxy. This will not be a violent crash like objects colliding on Earth. The distances between stars are so large that direct collisions are unlikely. Instead, it will be a long, graceful dance lasting hundreds of millions of years. For now, the Milky Way continues its slow rotation. Our Sun completes one orbit around the galaxy approximately every 225 to 250 million years. This journey is called a galactic year. Since the Earth formed, the Sun has completed only about 20 of these orbits. As the Sun moves, it carries with it the planets, asteroids, comets, and dust of our solar system. We are all traveling together through space, even when we feel still. The galaxy is filled with regions of calm and activity. Some areas are quiet, populated by older stars that burn gently and steadily. Other regions are turbulent, filled with supernova remnants, where massive stars have ended their lives in brilliant explosions, scattering heavy elements across space. These elements, forged in stars, are the building blocks of planets, oceans, and even life itself. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all formed long ago inside stars, within galaxies like the Milky Way. This connection is one of the most soothing truths in astronomy. We are not separate from the galaxy. We are shaped by it. As you rest now, imagine the Milky Way not as something distant, but as something that holds you gently within it. A vast structure, yes, but one that moves slowly, patiently, over timescales far longer than human worry or hurry. As your thoughts continue to drift gently outward, imagine the Milky Way not as a distant photograph, but as a living structure you are slowly floating through. There is no wind here, no sound, only motion, so gradual it feels like stillness. This is the natural pace of a galaxy. The Milky Way is often described as a barred spiral galaxy. This means that at its center, instead of a simple round bulge, there is a long, bar-shaped region made of stars. From the ends of this bar, spiral arms unfold and curve outward, wrapping around the galaxy like soft ribbons of light. These spiral arms are not solid structures. They are more like traffic patterns in space, regions where stars and gas tend to gather as they orbit the center. As material moves through these arms, clouds of gas are compressed, triggering the birth of new stars. This is why spiral arms glow more brightly than other parts of the galaxy. There are several major spiral arms in the Milky Way. Among them are the Perseus arm, the Sagittarius arm, the Scutums, Centaurus arm, and the Norma arm. Each one stretches across tens of thousands of light years, containing stars at different stages of life. Our solar system rests in a smaller structure between two major arms. The Orion Arm. This location is calm and relatively stable, far from the intense gravitational disturbances near the galaxy's core. It is one of the reasons life on Earth has had time to develop without frequent cosmic disruptions. If you could rise above the galaxy and look down upon it, the Milky Way would appear thin and wide, like a cosmic disk. Its diameter is roughly 100,000 light-years, but its thickness is only about 1,000 light-years in most places. This thinness is why the galaxy appears as a band across the sky when viewed from Earth. Beyond the bright disk lies a quieter region known as the galactic halo. The halo is a vast spherical space surrounding the Milky Way, filled with older stars, globular clusters, and an invisible component called dark matter. This halo extends far beyond the visible edges of the galaxy, holding it together with gravity. Globular clusters are among the oldest objects in the Milky Way. They are dense, spherical collections of hundreds of thousands of stars, all bound closely together. Many of these stars formed more than 10 billion years ago, shortly after the galaxy itself began to take shape. These clusters orbit the galaxy slowly, like lanterns drifting around a city. They do not belong to the spiral arms and contain very little gas or dust. Their stars are old, steady, and long-lived, adding a sense of quiet endurance to the galaxy's structure. The halo is also where much of the Milky Way's dark matter is believed to reside. Dark matter does not emit or reflect light, making it invisible to telescopes. Yet, its gravitational influence is essential. Without it, the galaxy would not rotate the way it does. Stars in the outer regions would drift away into space. Scientists estimate that dark matter makes up most of the galaxy's mass. It forms an unseen framework, guiding the motion of stars and gas like a gentle but firm hand. Though mysterious, dark matter contributes to the galaxy's stability, allowing its slow, graceful rotation to continue over billions of years. Closer to the center, the galaxy becomes more crowded. Stars are packed tightly together, and radiation levels are higher. Massive stars form and die more frequently here, enriching the surrounding space with heavy elements, but also creating a harsher environment. Despite this activity, the galactic center is not chaotic in the way we might imagine. Stars follow predictable orbits influenced by gravity rather than chance. Even near the supermassive black hole, motion follows quiet mathematical rules, traced carefully by astronomers over decades of observation. The Milky Way rotates, but not like a solid object. Different parts move at different speeds. Stars closer to the center complete their orbits faster than those farther out. This differential rotation helps maintain the spiral pattern, preventing it from winding too tightly. Our Sun moves through the galaxy at an average speed of about 220 kilometers per second. Yet, because everything around us is moving too, this motion feels perfectly calm. There is no sensation of speed, no rushing wind, only the steady passage of time. As the Sun travels, it oscillates slightly up and down through the galactic disk like a slow wave. Over millions of years, it passes through regions with varying densities of stars and gas. Some scientists study whether these movements influence long-term patterns on Earth, though the connections are subtle and complex. The Milky Way is not a fixed shape. Over cosmic time, its arms shift, its stars migrate, and its interactions with smaller galaxies leave gentle marks. Dwarf galaxies orbit and are sometimes absorbed, their stars becoming part of the halo or disk. These mergers are slow and quiet, unfolding over hundreds of millions of years. They add to the galaxy's mass and diversity, like layers in a deep, ancient story. As you rest now, imagine floating above this vast structure. The spiral arms glow softly. The halo stretches far into darkness. Everything moves, but nothing rushes. The Milky Way is not a place of constant drama. It is a place of balance, shaped by gravity, time, and patience. As we continue drifting through the Milky Way, let your attention move gently from the vast shape of the galaxy to the countless points of light within it. Each star you see, whether faint or bright, follows a long, patient story. Stars are not rushed creations. They are born slowly, live steadily, and end their lives over timescales that stretch far beyond human memory. Within the spiral arms of the Milky Way lie enormous clouds of gas and dust known as nebulae. These regions are calm, but full of potential, made mostly of hydrogen, with traces of helium and heavier elements. Nebulae drift quietly through space until gravity begins to pull them inward. Over time, small disturbances cause parts of these clouds. This collapse is slow and gentle, guided by gravity rather than force. As the material gathers, it warms. Eventually, a dense core forms, known as a protostar. At this stage, the star has not yet begun to shine. It is still gathering itself, quietly preparing. When the temperature at the core becomes high enough, nuclear fusion begins. Hydrogen atoms fuse into helium, releasing energy in the process. This moment marks the birth of a true star. Light begins its long journey outward, traveling through layers of gas before escaping into space. Most stars in the Milky Way spend the majority of their lives in this stable phase, known as the main sequence. Our Sun is a main sequence star, calmly converting hydrogen into helium, shining steadily without dramatic change. It has done so for about 4.6 billion years and will continue for billions more. Stars vary greatly in size, temperature, and brightness. Some are much smaller than the Sun, known as red dwarfs. These stars burn their fuel slowly and can live for trillions of years, longer than the current age of the universe. They shine faintly but reliably, contributing quietly to the galaxy's light. Other stars are massive and bright, burning through their fuel much more quickly. These giants shine intensely, illuminating nearby space, but their lives are short by cosmic standards. They may exist for only a few million years before reaching their end. The color of a star tells us much about it. Blue stars are hot and massive, radiating enormous amounts of energy. Yellow stars, like the Sun, are moderate in temperature. Red stars are cooler, often larger in size, but less intense in brightness. These colors create the soft variety of light scattered across the Milky Way. As stars age, they change. When a star, like the Sun, begins to run low on hydrogen. Its core contracts slightly, while its outer layers expand. It becomes a red giant, glowing warmly and shedding material into space. Eventually, it releases its outer layers entirely, forming a planetary nebula. At the center of this glowing shell remains a white dwarf, a dense, Earth-sized remnant that slowly cools over billions of years. It no longer produces energy through fusion, but it still radiates gentle heat, fading gradually into darkness. More massive stars follow a different path. When they exhaust their fuel, their cores collapse suddenly, triggering a supernova. This explosion briefly outshines entire galaxies, scattering heavy elements across space. These elements become part of new stars, planets, and life forms. Supernova are dramatic events, but they are also acts of creation. Without them, elements like iron, gold, and oxygen would be rare. The Milky Way owes much of its chemical richness to these rare but powerful moments. After a supernova, what remains depends on the star's mass. Some leave behind neutron stars, incredibly dense objects where matter is packed tightly together. Others form black holes, regions of space where gravity is so strong that not even light can escape. Despite their dramatic origins, these remnants often exist quietly afterward. Neutron stars rotate steadily, emitting beams of radiation like cosmic lighthouses. Black holes remain invisible, interacting with their surroundings only through gravity. Throughout the Milky Way, stars are born and die at different times, creating a layered history. Some stars formed shortly after the galaxy itself, while others are still taking shape today. This continuous cycle gives the galaxy a sense of renewal and balance. Star clusters offer a peaceful way to observe this process. Open clusters contain young stars formed together, drifting apart slowly over time. Globular clusters contain ancient stars, packed tightly and moving in graceful orbits around the galactic center. When you look up at the night sky, you are seeing stars at different distances and ages, all at once. Some are nearby neighbors. Others are far across the galaxy, their light softened by dust and time. This mixture creates the Milky Way's soft, textured glow. As you rest now, imagine each star as a steady breath of light, shining without effort, following a quiet path set by gravity and time. No star hurries. No star resists change. As we continue drifting gently through the galaxy, let your attention settle closer to home. Among the hundreds of billions of stars in the Milky Way, one modest yellow star carries with it a small family of planets, moons, and drifting dust. This star is our Sun, and its journey through the galaxy is calm, steady, and unhurried. The Sun is not fixed in place. It moves along with the rest of the Milky Way, orbiting the galactic center at a great distance. This orbit is wide and gentle, tracing a path that takes roughly 225 to 250 million years to complete. This immense span of time is known as a galactic year. Since life first appeared on Earth, the Sun has completed only a handful of these galactic orbits. Dinosaurs rose and disappeared during less than one full journey around the galaxy. Human history occupies only the tiniest fraction of a single orbit. This perspective invites patience. The galaxy does not measure time the way we do. Our sun's path is not a perfect circle. It gently weaves inward and outward, influenced by the mass of spiral arms and the gravitational pull of nearby stars. At the same time, it moves slightly above and below the galactic disk, oscillating like a slow wave over tens of millions of years. These movements are subtle. There is no sudden change, no sharp turn. Everything unfolds smoothly, guided by gravity, acting quietly across vast distances. The solar system moves as one, planets and all, held together by the sun's steady pull. The region of the galaxy we travel through is relatively peaceful. The Orion Arm contains fewer massive stars than the galaxy's inner regions. This reduces exposure to intense radiation and frequent supernova, creating a stable environment where complex life has time to develop. Some astronomers refer to this area as part of a broader galactic habitable zone. This does not mean life exists everywhere here, but that conditions are favorable. Heavy elements are present, radiation levels are moderate, and long-term stability is more likely. As the sun travels, it occasionally passes through clouds of interstellar gas and dust. These encounters are gentle and spread over millions of years. The heliosphere, a bubble formed by the solar wind, protects the planets by deflecting much of this material. The heliosphere itself is shaped by the sun's motion through the galaxy. It stretches out behind us like a soft tail, marking our path through interstellar space. Even at the edge of the solar system, the sun's influence can be felt. Comets, asteroids, and distant icy objects accompany us on this journey. Some are nudged gently by passing stars or galactic tides, occasionally drifting inward toward the sun. These events are rare and unfold slowly, adding subtle variety to the solar system's long history. The sun's motion through the Milky Way also connects us to distant stars. Over millions of years, our stellar neighbors change. Stars that are nearby today will drift away, while others will approach, each following their own calm orbits. Despite this constant motion, the night sky appears largely unchanged within a human lifetime. Constellations shift imperceptibly, reminding us that stability is often the result of slow change rather than stillness. When you look at the Milky Way from Earth, you are seeing the plane of the galaxy edge on. The brighter, thicker sections correspond to regions rich in stars and dust. The darker patches are clouds that block light, creating soft patterns across the sky. These dark lanes are not empty. They are filled with cold gas and dust, potential sites of future star formation. Even in darkness, the galaxy prepares quietly for what comes next. As the sun continues its orbit, it carries Earth through seasons of galactic environment. Some scientists study whether passing through spiral arms influences comet activity or climate over deep time. These connections remain areas of gentle curiosity rather than certainty. What is clear is that the sun's journey has been remarkably stable. This steadiness has allowed oceans to persist, climates to balance, and life to explore complexity without constant cosmic interruption. As you rest now, imagine the solar system drifting through the galaxy like a leaf floating on a wide, slow river. The river moves, but the leaf feels only a gentle current. It is part of a vast ordered motion that has unfolded quietly for billions of years. As your thoughts drift outward once more, imagine the Milky Way not as a solitary island of stars, but as part of a gentle, cosmic neighborhood. Space is vast, yet galaxies are not evenly scattered. They gather in families, bound together by gravity, moving slowly in relation to one another across immense stretches of time. Our galaxy belongs to a small collection known as the local group. This group contains more than 50 galaxies, though most are faint dwarf galaxies, small and subtle compared to the Milky Way. Together, they form a quiet community drifting through the universe. The largest companion to the Milky Way is the Andromeda Galaxy. It is slightly bigger than our own and lies about 2.5 million light-years away. On a clear, dark night, Andromeda can be seen with the naked eye as a faint oval glow, making it the most distant object visible without optical aid. Though Andromeda seems distant and still, it is moving toward us at a gentle pace. In roughly 4 billion years, they will begin to interact more directly, entering a long and graceful process of merging. This event is often described as a collision, but that word suggests violence and speed. In reality, galaxies are mostly empty space. Stars are separated by vast distances, and direct impacts between stars are extremely unlikely. Instead, the merger will be a slow rearranging of orbits, lasting hundreds of millions of years. As the Milky Way and Andromeda pass through one another, their spiral shapes will stretch and distort, forming long streams of stars. Over time, they will settle into a new structure, possibly an elliptical galaxy, calmer and rounder than either spiral was before. From within the galaxies, the night sky would change gradually. New patterns of stars would appear, bright arcs and soft glows forming over countless generations. Any planets that still exist would continue their orbits, largely unaffected by the distant motions of other stars. Another notable neighbor is the Triangulum Galaxy, smaller than both the Milky Way and Andromeda. It too is part of this quiet dance, influenced by the gravity of its larger companions. Together, these three galaxies shape much of the local group's structure. Surrounding them are many dwarf galaxies, some orbiting the Milky Way directly. The large and small Magellanic Clouds are among the most prominent. These irregular galaxies are visible from the southern hemisphere, drifting companions bound to our own. Over time, some dwarf galaxies are slowly absorbed into the Milky Way. There, stars are stretched into long streams that wrap around the galaxy, becoming part of its halo. These stellar streams are faint and delicate, traces of past encounters preserved in motion. Astronomers study these streams to understand the Milky Way's history. Each one tells a story of a small galaxy drawn in by gravity, its stars redistributed rather than destroyed. This process adds to the galaxy's mass and diversity, quietly reshaping it over time. Beyond the local group lies the Virgo supercluster, a much larger structure containing thousands of galaxies. Even this supercluster is part of an even greater cosmic web, where matter forms filaments and vast empty regions called voids. On these enormous scales, motion is slow and orderly. Galaxies drift along gravitational pathways shaped by dark matter. Nothing rushes. Everything unfolds over timescales so long that they feel timeless. The Milky Way itself moves within this larger structure, drawn gently toward a region known as the Great Attractor. This motion is subtle, shared by many nearby galaxies, like leaves carried together by a wide, invisible current. Despite all this movement, there is a deep sense of calm in the cosmic neighborhood. Galaxies interact rarely and slowly. Even dramatic events, when viewed from a galactic perspective, become quiet transitions rather than sudden disruptions. As you rest now, imagine the Milky Way as a softly glowing island drifting among others in a dark, silent sea. Each galaxy carries its own history, its own stars, its own possibilities, yet none exist alone. This connectedness extends inward as well. The atoms in your body were shaped by stars in ancient galaxies. The light reaching your eyes tonight may have traveled from a neighbor far beyond our own. As your breathing settles into a slow, steady rhythm, let your thoughts turn toward something unseen, yet profoundly important. Much of what shapes the Milky Way cannot be observed directly. It does not glow, sparkle, or emit light of any kind. And yet, without it, our galaxy would not exist in the way it does. This quiet presence is known as dark matter. Dark matter makes up most of the mass of the Milky Way, while stars, planets, gas, and dust account for everything we can see. They represent only a small fraction of the galaxy's true weight. The rest is invisible, detectable only through its gravitational influence. Astronomers first suspected the existence of dark matter when they studied how galaxies rotate. In the Milky Way, stars far from the center orbit at nearly the same speed as stars much closer in. According to the visible mass alone, the outer stars should move more slowly, but they do not. This unexpected motion suggests there is far more mass present than we can see. Something unseen is holding the galaxy together, preventing its outer regions from drifting away into space. That something is dark matter, forming a vast halo around the Milky Way. This halo extends far beyond the visible disk of stars, enveloping the galaxy like a gentle, unseen cocoon. Within it, the luminous parts of the galaxy are embedded, their motions guided by gravity rather than light. Dark matter does not interact with electromagnetic radiation. It does not absorb light, reflect it, or emit it. This makes it extraordinarily difficult to study directly. Scientists cannot photograph it, but they can map its effects by observing how galaxies behave. Through careful measurements, astronomers have determined that dark matter outweighs normal matter by roughly 5-to-1. This means most of the universe's structure is built upon something fundamentally invisible. The Milky Way's spiral shape depends on this hidden framework. Dark matter provides the gravitational stability that allows spiral arms to persist over long periods. Without it, the galaxy might have torn itself apart long ago. Dark matter also plays a crucial role in galaxy formation. In the early universe, it began clumping together before ordinary matter did. These clumps acted as gravitational seeds, drawing in gas that eventually formed stars and galaxies. In this sense, dark matter came first. It prepared the quiet scaffolding upon which the visible universe was built. The stars followed, lighting up structures that already existed in shadow. Even today, the Milky Way continues to move through its dark matter halo. As the galaxy travels through space, it carries this invisible mass with it, shaping its interactions with other galaxies and cosmic structures. Scientists are still searching for the true nature of dark matter. Many theories suggest it consists of exotic particles that rarely interact with normal matter. Experiments deep underground and in space attempt to detect these particles directly, shielding their instruments from other interference. So far, dark matter has remained elusive, yet its presence is undeniable. Every rotation curve, every gravitational lens, every large-scale map of the universe points to its influence. Closer to home, dark matter passes through the Earth constantly. If it is made of particles, they drift silently through your body, through walls and oceans, unnoticed. This may sound unsettling, but it is entirely harmless, interacting so weakly that it leaves no trace. There is something strangely comforting about this idea. The universe contains layers beyond what we can perceive, quietly shaping reality without demanding attention. The Milky Way's dark matter halo also affects its future. When the galaxy eventually merges with Andromeda, their halos will interact first, long before the stars themselves draw close. This slow gravitational embrace will guide the merger's overall shape and timing. Even the dwarf galaxies orbiting the Milky Way are influenced by this unseen mass. Their paths curve and shift according to the dark matter distribution, revealing its shape indirectly through motion. Despite its mystery, dark matter has become a cornerstone of modern astronomy and cosmology. It connects the smallest galaxies to the largest cosmic structures, providing continuity and coherence across vast scales. As you rest now, imagine the Milky Way not just as a luminous spiral, but as a glowing form suspended within an invisible ocean. The stars are like lanterns floating in a sea of gravity, their positions gently guided by something beyond sight. As the Milky Way slowly turns in your imagination, let your thoughts drift inward toward its very center. Far beyond the familiar stars of our night sky, hidden behind thick clouds of gas and dust, lies the galactic core. It is a region dense with stars, energy, and mystery, yet at its heart rests something remarkably calm. At the center of the Milky Way is a supermassive black hole known as Sagittarius, often spoken softly as Sagittarius, a star. Despite the dramatic reputation of black holes, this one is not a cosmic monster tearing everything apart. Instead, it is quiet, stable, and surprisingly gentle on astronomical timescales. Sagittarius A has a mass about 4 million times that of the Sun. While this number sounds enormous, it is relatively modest compared to the black holes found in some other galaxies. Many galaxies host black holes billions of times more massive than our own. This black hole sits approximately 26,000 light-years away from Earth, in the direction of the constellations Sagittarius. From our perspective, it is hidden behind layers of interstellar dust which block visible light. Astronomers observe it using radio waves, infrared light, and X-rays that can pass through this cosmic veil. The evidence for Sagittarius A comes not from seeing the black hole itself, but from watching how nearby stars move. Over decades, astronomers have tracked stars orbiting an invisible point with incredible precision. These stars move extremely fast, following tight elliptical paths. One of the most famous of these stars completes an orbit in just 16 years, moving at thousands of kilometers per second when closest to the center. Such speeds can only be explained by the presence of a very massive, compact object. No other known structure fits the observations as perfectly as a supermassive black hole. Despite its mass, Sagittarius A is relatively small in physical size. Its event horizon, the boundary beyond which nothing can escape, is only about the size of Mercury's orbit. In a galaxy spanning over 100,000 light-years, this is a tiny region. What makes Sagittarius a peaceful is its low activity level. It is not currently consuming large amounts of matter. When gas or dust falls toward it, the material heats up and emits radiation. But this happens infrequently and gently compared to active galaxies. Because of this calm behavior, life in the Milky Way is not constantly bombarded by intense radiation from the center. This stability may have played an important role in allowing complex life to develop over billions of years. Surrounding the black hole is a crowded region called the galactic bulge. Here, stars are packed far more densely than in our local neighborhood. Some estimates suggest millions of stars exist within just a few light-years of the center. These stars tend to be older and richer in heavy elements formed from generations of stellar recycling. Their light contributes to the soft glow observed in infrared images of the galaxy's core. Interwoven among these stars are powerful magnetic fields, swirling gas clouds, and occasional bursts of energy. Even in its calm state, the galactic center is a place of subtle motion and quiet intensity. Every so often, Sagittarius flares briefly as small amounts of matter fall inward. These flares are detected by space telescopes and serve as reminders that the black hole is still very much alive, quietly shaping its surroundings. Black holes like Sagittarius A are now thought to exist at the centers of most large galaxies. Their mass is closely linked to the mass of the galaxy itself, suggesting a deep connection between galaxy formation and black hole growth. This relationship hints that black holes and galaxies evolve together, influencing one another over a cosmic time. The Milky Way and its central black hole are partners in a long, slow dance spanning billions of years. Interestingly, Sagittarius A is not directly dangerous to us. Its gravitational pull weakens with distance, just like that of any other object. At Earth's distance, it has no more effect on us than any other mass of similar size would. You are far more influenced by the Sun, the Earth, and even the Moon than by the black hole at the center of the galaxy. This makes the idea of a supermassive black hole less frightening and more quietly fascinating. As you rest now, imagine the Milky Way rotating gently around this calm center. Billions of stars follow their paths, guided by gravity, unaware of the slow heartbeat at the core. As we drift outward from the calm center of the Milky Way, the galaxy slowly opens into vast, graceful spiral arms. These arms are not solid structures, but regions of higher density, gently sweeping through the galactic disk like slow-moving waves. Within them, stars are born, planets take shape, and the familiar elements of life are quietly assembled. The Milky Way is classified as a barred spiral galaxy. This means that at its center lies a long bar of stars, from which the spiral arms extend outward. Astronomers believe our galaxy has 4 main spiral arms, along with several smaller spurs and branches that weave between them. These spiral arms are named Perseus, Scutums, Sagittarius, and Norma. Our own solar system resides in a smaller structure called the Orion Arm, sometimes referred to as the Orion Spur. It is a relatively quiet neighborhood, positioned between 2 major arms. Spiral arms are especially important because they are rich in gas and dust. These materials are the raw ingredients for star formation. As the density wave of a spiral arm passes through the galaxy, it gently compresses clouds of gas, triggering the slow collapse that leads to new stars. In these stellar nurseries, gravity works patiently. Over millions of years, clouds fragment, cores grow denser, and temperatures rise. Eventually, nuclear fusion ignites, and a new star begins to shine. This process continues today, just as it has for billions of years. Some of the most beautiful sights in astronomy are found within spiral arms. Bright, blue stars, short-lived and massive, illuminate surrounding gas clouds. Their intense radiation causes nebulae to glow in shades of pink, red, and violet, creating the soft cosmic colors captured by space telescopes. Famous regions such as the Orion Nebula, Eagle Nebula, and Carina Nebula are all located within spiral arms. These places are not just visually stunning. They are active laboratories of astrophysics, teaching us how stars and planetary systems form. The spiral arms also contain many open star clusters. These are groups of stars born together from the same cloud. Over time, gravitational interactions slowly pull these clusters apart, scattering their stars across the galaxy. While spiral arms are places of creation, they are also shaped by destruction. Massive stars live fast and die young, ending their lives in supernova explosions. These events spread heavy elements like carbon, oxygen, and iron into space. Those elements later become part of new stars, planets, and eventually living organisms. Every atom of calcium in your bones and iron in your blood was once forged in the heart of a star within a spiral arm. This recycling of matter is one of the most calming truths about the universe. Nothing is wasted. Everything transforms slowly and purposefully across cosmic time. Our location in the Orion Arm offers a relatively stable environment. We are far from the crowded galactic center, reducing exposure to intense radiation. At the same time, we are close enough to star-forming regions to benefit from enriched elements. This balance may be one reason Earth developed complex life. The spiral arms provide opportunity, while distance provides safety. It is a quiet compromise written into the structure of the galaxy itself. The Sun takes about 230 million years to complete one orbit around the Milky Way. Since its formation, it has made roughly 20 such journeys. During these orbits, it has gently moved in and out of spiral arms, experiencing different galactic neighborhoods. Some scientists suggest that passing through dense spiral arms may influence climate or biodiversity on long time scales, though these effects are subtle and still being studied. From afar, spiral arms give galaxies their iconic appearance. From within, they are vast, diffuse, and slow-moving. There is no sudden motion, no dramatic rotation visible to the naked eye. Everything unfolds gradually. If you could watch the Milky Way over millions of years, you would see arms shifting, stars drifting, and patterns evolving like a cosmic tide. Nothing rushes, nothing stops. As you relax now, imagine floating between stars in one of these spiral arms. Around you, clouds glow faintly. Young stars shine softly. Older stars drift peacefully, carrying the memory of earlier times. As we continue drifting through the Milky Way, the spiral arms slowly fade into the background, and our attention turns to the stars themselves. Each one you see in the night sky is living through a long, quiet story, shaped by gravity, time, and balance. These stellar life cycles unfold so slowly that even dramatic events feel calm when viewed on a cosmic scale. Every star begins its life inside a nebula, a vast cloud of gas and dust suspended in space. These clouds are often cold and dark, drifting for millions of years before anything stirs. Then, gradually, gravity begins to gather material into denser regions, pulling atoms closer together. As a cloud collapses, it spins gently, flattening into a disk. At its center, pressure and temperature rise. When the core becomes hot enough, hydrogen atoms begin to fuse into helium. This moment marks the birth of a star. Once fusion begins, a star enters its longest and most stable phase, known as the main sequence. Our Sun has been in this stage for about 4.6 billion years and will remain there for billions more. During this time, stars maintain a delicate balance between gravity pulling inward and energy pushing outward. Stars on the main sequence vary widely. Small red dwarfs burn their fuel slowly, glowing faintly but enduring for trillions of years. Massive blue stars burn intensely, shining brilliantly but living only a few million years before exhausting their fuel. Red dwarfs are the most common stars in the Milky Way. Though faint, they are incredibly long-lived. Many that formed early in the universe are still shining today, quietly stable and unchanging. Larger stars live faster lives. Their greater mass creates higher pressure in their cores, accelerating nuclear fusion. These stars produce heavier elements more quickly, but run out of fuel sooner. When a star like the Sun begins to exhaust its hydrogen, its core contracts while its outer layers expand. The star becomes a red giant, growing large and luminous. From a distance, this transformation is slow and graceful. In the far future, the Sun will expand enough to engulf Mercury and Venus, and possibly Earth. Yet even this dramatic event will unfold over hundreds of millions of years without sudden violence. Eventually, a Sun-like star sheds its outer layers, forming a planetary nebula. Despite the name, these glowing shells have nothing to do with planets. They are delicate clouds illuminated by the star's remaining core. What remains is a white dwarf, a dense Earth-sized remnant slowly cooling over billions of years. It no longer produces energy, but continues to glow faintly, radiating stored heat into space. More massive stars follow a different path. After becoming red supergiants, they begin fusing heavier elements in layers, like an onion. Iron forms at the core, and fusion stops. Gravity then overwhelms the star. The result is a supernova explosion, one of the most energetic events in the universe. For a brief time, a single star can outshine an entire galaxy. Yet, even this immense release of energy happens within the larger calm of space. Supernova scatter heavy elements across the galaxy. Gold, uranium, and many elements essential to modern technology are created in these moments. The devices that power communication, education, and global economy all rely on atoms forged in ancient stars. After the explosion, the star's core remains as either a neutron star or a black hole. Neutron stars are incredibly dense, spinning rapidly and emitting beams of radiation like cosmic lighthouses. Black holes are regions where gravity becomes so strong that not even light escapes. Despite their dramatic reputation, most black holes are quiet, slowly interacting with their surroundings. These remnants are not endings, but transitions. The matter released becomes part of new clouds, new stars, and new planetary systems. The Milky Way continually renews itself through these cycles. Star formation and death shape the structure of the galaxy. They influence where planets form, how chemistry evolves, and where life might emerge. From a peaceful perspective, stars live lives of balance and transformation. Nothing is wasted. Nothing truly disappears. As you rest now, imagine stars being born, shining for eons and gently fading, all while the galaxy drifts around them. Their stories are long, patient, and steady. As we continue our gentle journey through the Milky Way, the stars around us no longer feel isolated. Many stars are not born alone, but as part of quiet families known as star clusters. These stellar neighborhoods drift through the galaxy together, bound by gravity and shared origins. Star clusters form when large regions of a nebula collapse at the same time. Rather than creating a single star, the cloud fragments into many smaller cores. Each core becomes a star, all igniting within a relatively short cosmic moment. There are two main types of star clusters: open clusters and globular clusters. Each tells a different story about the galaxy's history and structure. Open clusters are loosely bound groups of young stars. They are often found in the spiral arms of galaxies, including our own. These regions are rich in gas and dust, making them ideal places for ongoing star formation. An open cluster might contain a few dozen stars or several thousand. They are spread out over large distances, and their gravitational bonds are relatively weak. Over time, interactions with other stars and galactic tides slowly pull them apart. One well-known open cluster is the Pleiades, sometimes called the Seven Sisters. Visible to the naked eye, this cluster has inspired myths and stories across cultures for thousands of years. It reminds us how astronomy, culture, and history quietly intertwine. Because open clusters are young, their stars often shine bright blue or white. These colors indicate high temperatures and relatively short lifespans. Many of these stars will evolve quickly, shaping their surroundings before drifting away. Globular clusters are very different. They are ancient, densely packed spheres containing hundreds of thousands, sometimes millions, of stars. These clusters orbit the Milky Way's core, forming a halo around the galaxy. Globular clusters are among the oldest known structures in the universe. Some are over 12 billion years old, formed shortly after galaxies themselves began taking shape. Studying them helps scientists understand early cosmic history. Within a globular cluster, stars are tightly packed. In the core, stars can be separated by distances smaller than the space between our Sun and its nearest neighbor. Despite this density, collisions are still rare due to the vastness of space. The stars in globular clusters tend to be older and redder. They contain fewer heavy elements, reflecting a time when the universe had not yet been enriched by generations of supernova. These clusters are living fossils of the early universe. Star clusters also play an important role in education and research, because all the stars in a cluster form at roughly the same time and distance. Astronomers can study how stars of different masses evolve under similar conditions. Beyond clusters, stars often form in smaller groups or binary systems. Many stars, including some similar to the Sun, have one or more stellar companions. These systems gently orbit each other, exchanging gravitational influence. Binary stars are especially important in astronomy. By observing their motions, scientists can calculate stellar masses, which helps refine models of stellar evolution and energy production. Some systems contain 3 or more stars, forming complex but stable arrangements. These multi-star systems can host planets, offering intriguing possibilities for diverse worlds. Our own Sun is relatively solitary, but it likely formed in an open cluster billions of years ago. Over time, its siblings drifted away, scattered throughout the Milky Way. Somewhere in the galaxy, stars born alongside the Sun still shine. Stellar neighborhoods influence planetary formation. Nearby massive stars can shape protoplanetary disks with radiation and stellar winds, affecting how planets form and what materials they contain. These processes connect astronomy with planetary science, chemistry, and even the foundations of future space travel and exploration. Understanding star clusters helps guide where astronomers search for exoplanets and potential life. As the Milky Way rotates, star clusters orbit along with it, slowly changing shape under gravitational forces. Some dissolve entirely, while others remain intact for billions of years. From a calm perspective, star clusters are reminders that the universe favors cooperation over isolation. Stars form together, evolve together, and often drift apart gently rather than violently. As you rest, imagine drifting through one of these clusters. Thousands of stars glow softly around you, each with its own story, yet all part of a shared origin. As we drift onward through the Milky Way, the stars slowly give way to vast, delicate clouds. These are nebulae, some of the most beautiful and peaceful structures in the galaxy. They are places where matter gathers, where light diffuses softly, and where time seems to move at a slower, gentler pace. Nebulae are enormous clouds of gas and dust, stretching across dozens or even hundreds of light years. Though they appear solid in images, they are incredibly thin. If you were inside a nebula, you would barely notice it, surrounded by particles spaced far apart. Most nebula are made primarily of hydrogen, the simplest and most abundant element in the universe. Alongside hydrogen are traces of helium, oxygen, carbon, and other elements forged in ancient stars. These ingredients quietly recycle through cosmic time. Some nebulae are known as stellar nurseries. Within them, gravity slowly pulls material together, forming dense regions that eventually ignite into new stars. This process unfolds over millions of years, unhurried and patient. The Orion Nebula is one of the most famous examples. Visible from Earth, it has been observed for centuries. Inside it, hundreds of young stars glow, surrounded by swirling gas, illuminated by their light. Other nebulae mark the end of a star's life. When a star like our Sun exhausts its fuel, it sheds its outer layers into space, creating a planetary nebula. Despite the name, these have nothing to do with planets. Early astronomers simply thought they resembled them. Planetary nebulae are often symmetrical and colorful, shaped by stellar winds and magnetic fields. They represent a quiet farewell, enriching the galaxy with heavier elements needed for future generations of stars and planets. There are also supernova remnants, nebulae formed from the explosive deaths of massive stars. These events are among the most energetic in the universe. Yet the remnants expand slowly afterward, forming intricate filaments and shells. The Crab Nebula is one such remnant, created by a supernova observed by astronomers nearly 1,000 years ago. Today, it continues to glow softly, energized by a rapidly spinning neutron star at its center. Nebulae appear in different colors depending on their composition and the energy passing through them. Red hues often come from glowing hydrogen, while blues may reflect starlight scattered by dust. These colors connect astronomy with physics and chemistry, offering insights into how matter behaves under extreme conditions. They also inspire art, design, and visual culture across the world. Dark nebulae are equally fascinating. Rather than glowing, they block light, appearing as silhouettes against brighter backgrounds. These dense regions hide star formation within, quietly shaping the future of the galaxy. The Milky Way contains thousands of known nebulae, each playing a role in the slow cycle of creation and transformation. Together, they form a breathing system, expanding and contracting across cosmic time. Nebulae also influence the economics of space, exploration, and technology. Understanding them helps protect spacecraft, guide telescope design, and refine models used in satellite communication and navigation. For those who enjoy travel and tourism, nebulae have become iconic symbols of cosmic wonder. Images from space telescopes inspire planetariums, museums, and educational programs around the world. As you imagine floating through a nebula, there is no sound, no urgency. Light spreads gently, and gravity whispers rather than pulls. It is a place of beginnings and endings, coexisting peacefully. Our own sun was born in such a cloud long ago. Every atom in your body once drifted through a nebula, making these structures deeply personal, even if they seem distant. Nebulae remind us that creation does not need speed or force. Sometimes, the most powerful changes happen quietly over long stretches of time. As we continue drifting through the Milky Way, the scene grows quieter still. Between stars and nebulae lies something easily overlooked, something subtle yet essential. This is cosmic dust, tiny grains, often smaller than a grain of smoke, scattered across immense distances, quietly shaping the structure and story of our galaxy. Cosmic dust is made of microscopic particles of carbon, silicates, ice, and metals. Though each grain is incredibly small, together they influence how galaxies evolve, how stars form, and how light travels through space. These dust particles form in the cooling atmospheres of dying stars. As stars shed material into space, atoms bond into molecules, and molecules slowly assemble into solid grains. Over millions of years, this dust drifts outward, becoming part of the galactic environment. Dust plays a vital role in star formation. Inside cold, dense clouds, dust helps block external radiation, allowing gas to cool. Cooler gas collapses more easily under gravity, eventually igniting into new stars. In this way, dust acts as a quiet facilitator of creation. Despite its importance, cosmic dust makes up only about 1% of the interstellar medium by mass. Gas dominates by far, yet dust has an outsized influence on temperature, chemistry, and visibility throughout the galaxy. Dust shapes how we see the Milky Way from Earth. It absorbs and scatters visible light, creating dark lanes across the galactic plane. These lanes are not empty space, but dense regions rich with hidden structure. Because dust blocks visible light, astronomers rely on infrared and radio observations to peer through it. This has driven advances in telescope technology, benefiting science, education, and even Earth-based imaging systems used in medicine and environmental monitoring. Dust grains also act as chemical meeting places. On their surfaces, atoms stick, interact, and form complex molecules, including water and organic compounds. Some scientists believe this process helped seed early planetary systems with the ingredients for life. Our own solar system formed from a disk rich in cosmic dust. Over time, grains collided, clumped together, and grew into rocks, then planets. Every mountain, ocean, and living cell on Earth carries a legacy that began as interstellar dust. When sunlight hits dust, it warms the grains slightly, causing them to emit infrared radiation. This gentle glow allows astronomers to map dust clouds across the galaxy, revealing hidden spiral arms and star-forming regions. Dust also influences climate on cosmic scales. By regulating how energy moves through galaxy, it affects star formation rates, galaxy brightness, and long-term evolution. Even at the largest scales, small things matter. In some regions, dust aligns with magnetic fields, polarizing light that passes through. By studying this effect, scientists map invisible magnetic structures that guide gas flow and shape nebulae. Cosmic dust connects astronomy with industry and technology. Research into dust behavior informs material science, nanotechnology, and even manufacturing processes where controlling tiny particles is essential. For space travel and exploration, dust is both a resource and a challenge. High-speed dust impacts can damage spacecraft, while dust accumulation affects instruments and solar panels. Understanding it helps improve spacecraft design and safety. In art and culture, cosmic dust has become a symbol of humility and connection. The phrase, "we are made of stardust," is not poetic exaggeration, but scientific fact, grounding human identity within the universe. As you imagine drifting among these tiny grains, there is a sense of calm in their patience. They do not rush. They move slowly, guided by gravity, radiation, and time itself. Cosmic dust teaches us that importance is not measured by size. Even the smallest components can influence vast systems, shaping galaxies and destinies alike. As this part gently fades, let the thought settle that every breath you take contains atoms once carried by interstellar dust. You are not separate from the galaxy, but a continuation of it. As we drift farther outward, the Milky Way begins to reveal its grand design. But from a distance, it would appear as a vast spiral, with long, graceful arms winding slowly around a glowing center. These spiral arms are not rigid structures. They are gentle rivers of stars, gas, and dust, flowing together through cosmic time. The Milky Way is classified as a barred spiral galaxy. At its heart lies a central bar of stars, from which spiral arms extend outward. These arms curve softly, wrapping around the galactic core, like luminous ribbons. Spiral arms are regions of slightly higher density, known as density waves. As stars and gas orbit the galaxy, they pass through these waves, much like cars moving through a slow traffic jam. The wave itself persists, even though the individual stars continue on their paths. Because gas clouds are compressed as they enter spiral arms, these regions are rich in star formation. Young, bright stars illuminate the arms, making them stand out against the darker spaces between. Our solar system resides in a smaller structure called the Orion Arm, or Orion Spur, located between two major arms known as Perseus and Sagittarius. This quieter neighborhood may have contributed to Earth's long-term stability. Spiral arms move slowly, completing a rotation around the galaxy in hundreds of millions of years. During that time, stars drift in and out of them, experiencing cycles of density and calm. The Sun takes about 225 to 250 million years to orbit the center of the Milky Way once. This journey is sometimes called a galactic year. Since Earth formed, the Sun has completed only about 20 such orbits. As stars pass through spiral arms, they may encounter more cosmic dust and radiation. Some scientists study whether these passages influence long-term climate patterns on planets, linking astronomy with geology and earth science. Spiral arms also guide the flow of gas throughout the galaxy. They help funnel material inward and outward, supporting the ongoing cycle of star birth and stellar death. In infrared light, spiral arms appear broader and smoother, revealing older stars hidden by dust. This shows that the Milky Way's structure is layered, with different populations tracing different histories. Understanding spiral structure has practical applications beyond astronomy. The mathematics used to model galactic motion appears in economics, traffic engineering, and systems analysis, showing how patterns emerge from large numbers of moving parts. Spiral galaxies like the Milky Way are common throughout the universe. Observing others helps astronomers infer our own galaxy's shape, even though we cannot see it directly from the outside. Some galaxies lose their spiral arms over time, becoming more chaotic or elliptical. The Milky Way's continued structure suggests a relatively calm merger history, favorable for long-term star and planet development. The spiral arms are not places of danger, but of renewal. They are regions where old material is reshaped into new stars, continuing a cycle billions of years old. As you imagine floating above the Milky Way, the arms appear serene and balanced, rotating slowly without urgency. Their motion is steady, predictable, and calming. These vast structures remind us that even enormous systems can move gracefully. There is no rush in the galaxy, only rhythm and repetition. As we drift inward along the spiral arms, the light slowly thickens. Stars grow more numerous, closer together, until the quiet openness of the outer galaxy gives way to a gentle crowding. We are approaching the heart of the Milky Way, a region both active and serene, where enormous forces exist in a steady, balanced state. The galactic center lies about 26,000 light-years from Earth, in the direction of the constellation Sagittarius. From our planet, it is hidden behind dense clouds of dust and gas, making it invisible to the naked eye. Yet even unseen, its presence shapes the motion of everything around it. At the very center of the Milky Way is a supermassive black hole known as Sagittarius. Despite its dramatic name, it is not a violent destroyer. It is calm, slow, and relatively quiet compared to black holes in more active galaxies. Sagittarius A has a mass about 4 million times that of our Sun. This immense gravity anchors the galaxy, guiding the orbits of stars across vast distances. Without it, the Milky Way structure would be far less stable. Black holes are regions where gravity is so strong that not even light can escape once it crosses a boundary called the event horizon. But outside that boundary, space behaves normally. Stars orbit Sagittarius peacefully, following predictable paths. Astronomers study these stellar orbits carefully by tracking how stars move near the galactic center. Scientists confirmed the black hole's existence and measured its mass with remarkable precision. This work blends observation, mathematics, and advanced technology. The galactic center is crowded with stars, including many old red giants and dense clusters formed long ago. These stars move quickly, responding to the strong gravitational pull at the core. Despite the density, collisions between stars are still rare. Space remains vast, even in the busiest regions. The overall feeling is not chaos, but quiet complexity. Surrounding the black hole is a disk of gas and dust, slowly rotating. Occasionally, small amounts of material fall inward, releasing gentle bursts of energy detectable in radio and infrared light. Unlike the dramatic black holes seen in distant quasars, Sagittarius A is relatively inactive. This calm may have allowed life-friendly conditions to persist in the outer regions of the galaxy, including our own neighborhood. The center of the Milky Way is also rich in exotic phenomena, shaping long filaments of charged particles that glow faintly in radio wavelengths. These magnetic structures help regulate how energy flows through the galaxy. They influence star formation, gas movement, and the overall balance between order and change. Studying the galactic center has driven innovation in telescope design. Instruments capable of piercing dust clouds have applications in Earth observation, climate monitoring, and even medical imaging. In cultural history, the center of the galaxy has inspired myths and philosophies across civilizations. Many ancient cultures imagined a cosmic axis or central point around which the heavens turned, echoing modern astronomical understanding. For space travel and future exploration, understanding galactic cores is essential. It helps scientists model radiation environments, gravitational dynamics, and long-term cosmic evolution. Though the center contains extreme gravity, it is not a place of constant destruction. Instead, it is a region of equilibrium where forces balance over immense timescales. As you imagine floating near the galactic core, there is no sound, no sudden motion. Stars glide along curved paths. Light bends gently, and time feels deep and unhurried. This calm at the center reflects a broader truth of the universe. Even where power is greatest, stability can emerge. Even where gravity is strongest, harmony can exist. The galactic center reminds us that strength does not require violence, and motion does not require chaos. Everything moves as it must, guided by invisible structure. As our journey through the Milky Way gently reaches its final moments, we drift outward once more, away from the bright density of the galactic center, back along the spiral arms, toward a familiar and peaceful region of space. This is where reflection naturally begins. After exploring stars, dust, nebulae, and motion on unimaginable scales, we arrive at a simple, calming truth. We are not separate from the galaxy. We belong to it. Earth exists on a small planet orbiting an average star, located in a quiet spur of one spiral arm. From a cosmic perspective, this is an unremarkable location. And yet, it is precisely this calm placement that has allowed complexity, stability, and life to emerge. The Milky Way contains hundreds of billions of stars. Among them are countless planetary systems, many with rocky worlds, oceans of ice, and atmospheres shaped by time. Modern astronomy suggests that planets are common, not rare, making the galaxy feel less empty and more gently populated. Our Sun formed about 4.6 billion years ago from a cloud enriched by earlier generations of stars. The iron in your blood, the calcium in your bones, and the oxygen you breathe were forged long before Earth existed. They traveled through space quietly, patiently, before becoming part of you. This connection between human life and cosmic history has reshaped education, philosophy, and culture. Science no longer places humanity outside the universe, but within it, woven into its processes. As our solar system orbits the galactic center, it passes through regions of varying density, light, and radiation. Yet over billions of years, these changes have been gradual, giving life time to adapt and evolve. The Milky Way itself is part of a larger structure called the Local Group, a small collection of galaxies bound together by gravity. Beyond that lies the Virgo supercluster, and beyond that, a vast cosmic web stretching across the observable universe. Despite this immensity, the night sky feels intimate. The stars you see are neighbors in galactic terms. They're light traveling distances that sound enormous but remains small compared to the size of the universe. Astronomy has influenced global cooperation in science, technology, and education. Telescopes are often international projects, bringing together researchers, engineers, and institutions across borders in quiet collaboration. Space science also shapes everyday life. Technologies developed for astronomy contribute to communication systems, navigation, imaging, and data analysis used across industries and economies. Culturally, the Milky Way has inspired stories for thousands of years. From ancient sky myths to modern science fiction, humanity has always looked upward, seeking meaning, comfort, and perspective. There is something deeply calming in realizing how long the universe has existed and how slowly it changes. Worries that feel heavy in the moment soften when placed against cosmic time. The Milky Way will continue rotating long after this moment. Stars will be born, age, and fade. Dust will gather. Light will travel. The galaxy does not rush. In about 4 billion years, the Milky Way will gently merge with the neighboring Andromeda galaxy. This will not be a violent collision, but a slow blending, unfolding over hundreds of millions of years, forming a new, larger galaxy. Even then, the universe will remain calm. On cosmic scales, change is patient. As you rest now, imagine Earth moving quietly through space, carried along by the steady motion of the Milky Way. There is no edge to fall from, no sudden stop, only continuous movement guided by gravity and time. You are supported by layers of structure, from Earth's surface to the Sun's gravity to the galaxy's spiral arms. Everything holds everything else. This final thought is perhaps the most comforting. You are not lost in the universe. You are held within it. As the stars continue their slow dance and the Milky Way turns gently in the dark, allow your thoughts to settle. Let the vastness bring peace, not distance. The galaxy does not demand attention. It simply exists quietly, patiently, offering perspective to those who look up. And now, as this journey comes to rest, you can drift as well, knowing that above you, around you, and within you, the universe continues its calm, endless motion. Thank you for traveling through the Milky Way. Rest well.